Hi guys, it's Daniel here, and today we're going to do the final problem of my USAMO practice test. So let's first read the problem. On a triangle ABC, we have DE and F be the tangency points of the incircle of ABC with sides BC, CA, and AB as shown in the diagram. And we also have another circle that's concentric with the incircle, such that it's also tangent with the EF. And M and N are the intersections of EF with the tangents from D to this incircle, as shown in the diagram. And we have to prove that D, X, M, and N are concyclic, where X is the midpoint of BC. So first, this diagram seems like an extremely hard to figure out diagram because you usually don't deal with things like having two concentric circles and having the second circle tangent to some random line. But let's see what sort of properties we can find from this diagram. So first off, I'll prove that dm equals em. And we can see this is true by first drawing that certain subsection of the diagram, this section with the concentric circles. So we have that E is right here, and M right here, and there is D, like so. So first we notice that if we draw the tangency points here, then MD and ME are both tangent to this smaller circle, omega 0. So that means these two lines are actually equal. And in addition, if we look at these two sections, they're also equal because they're half the length of the chord of the incircle that's also tangent to the smaller circle. So each of those segments is half of this chord, and this chord is uniquely defined as a certain length. So that means these two marked lengths are also equal. So therefore, since M to the tangency point is equal and the tangency point to E is equal with M to the other tangency point to D, that means dm equals em. So that's actually very nice because we also notice that CE equals CD. And this is true because CE and CD are both common tangents from C to the incircle. And so since CE equals CD, ME equals MD, and of course we also have MC is trivially equal to MC, then we actually get that triangle CEM is congruent to triangle CDM. And what's nice about this? Well, this actually tells us that if we draw CM, then since the two triangles are congruent, we get that this angle is equal to this angle. So in fact, CM passes through the incenter I. So CI M are collinear. And through an identical argument, we can also show that B, I, and N are collinear as well. So now we've got some much easier to work with information. We like collinearities much better than some random concentric circles. Well, now that we have these collinearities, we can in fact just totally ignore the smaller circle omega 0 because we note that M and N are also just defined as the intersections of BI and CI with EF. So let's just draw another diagram that reflects this. So we have triangle ABC with an incircle, that is. Okay, that was a really bad one. There, incircle. There, a lot better. Incircle with this is E, this is F, this is D, And we have this line EF. And now we intersect the in-center I, CI, with it to get M. And we intersect BI to get N. Alright, now that we've had this M and N cleared up a bit, let's try drawing MD back in again. So we had MD on our original diagram, so we have MD now. So now what do we notice about this diagram? Well, for one, the quadrilateral BDMF kind of looks cyclic. So let's see if we can prove that it's cyclic. And to do this, we'll use, of course, angle chasing. So BDM, this angle, is equal to this angle. And the reason why is because remember that triangle CEM is congruent to triangle CDM, which means that angle MDC is equal to angle MEC. And once these two angles are equal, obviously angle BDM is equal to angle MEA because they're supplementary of these two equal angles. So now we know that these two angles are equal. However, we also know that angle MEA is equal to angle EFA because triangle AFE is isosceles. Because AF equals AE, they're both common external tangents to the incircle from A. So now, since angle AFE is equal to angle MDB, we see that this angle MFB is in fact supplementary to angle MDB, which means that triangle BDMF is cyclic. So let's draw that in. And now we also note that the circumcircle of triangle BFD also passes through the incenter because BFI is equal to 90 degrees and the angle BDI is equal to 90 degrees. So in fact, the circle BI is the diameter of this circle. So now we know that angle BMI is also equal to 90 degrees because M also lies on this circle. So BMI equals 90 degrees. And similarly, we can prove that angle CNI is equal to 90 degrees. It's exactly the same argument, but on the other side. So now we know that BMI and CNI are both equal to 90 degrees. So that suggests us to try to extend BM and CN to hit at, I don't know, a point P. Because that would make I the orthocenter of triangle BCP. So now I is the orthocenter of triangle BCP. And that's good because now we know, well, this diagram isn't very accurate, but since I is the orthocenter of BCP, then we know that the line PI is bisects, or not bisects, is perpendicular to BC. And since ID is perpendicular to BC, we know that PID also lie on a line. So now we have this we have this triangle with BCP with M, N, and D as the feet of the altitudes from C, B, and P respectively. But then remember that we're trying to prove that M and D in the midpoint of BC, call it X, are concyclic. And what do we know about the circle that passes through the feet of the altitudes? This circle is a special circle. It is actually the 9-point circle of triangle BCP. And for those of you who don't know what the 9-point circle is, it's basically if you have a triangle that, let's draw it here. If you have a triangle and if you mark the midpoints of the sides, the feet of the altitudes, like so, and also, oops, those are supposed to be concurrent. And also the midpoints of the segments AH, BH, and CH, i.e. the segments from the vertices to the orthocenter. If you mark these midpoints, then these 9 points all lie on one circle called the 9-point circle. And the very definition of the 9-point circle finishes the problem off for us, because since X is the midpoint of BC, it must lie on the 9-point circle of triangle BCP. Except the circumcircle of DMN is also the 9-point circle. So therefore, X lies on the circumcircle of DMN. So X, DMN are all concyclic, and we are done.
Hey guys, Zong here, back with another math video. For the past few weeks we've been doing USIMO problems, but Daniel wanted to do his last one, and